All right. So before we continue with solving quadratic equations, which we were doing at the tail end of this last section, I want to take a quick detour and discuss something called complex numbers. So even though the name sounds intimidating, it's really not. So the way that complex numbers work is this. So in the past, you may have been told that you cannot take the square root of a negative number. This section is to show you that this is not necessarily the case. So let's go ahead and define what a complex number is. A complex number is any number written in this form, a plus bi, where a and b are real numbers, and I is equal to the square root of -1. So there are multiple parts to this. In a complex number, a is called the real part. The number b is called the imaginary part. And I is what's known as the imaginary unit. So for example, I is a complex number. 1 plus 2i is a complex number. 3 square root of 2 times I is a complex number. 5 is a complex number. Now, why would it be a complex number? Well, truth is, we can write any number as a complex number, even real numbers, right? For example, I could write 5 as 5 plus 0 times I, because 0 times anything is just 0. So remember, in the beginning of the year, we talked about the hierarchy of numbers. You had natural numbers, then you had integers, then you had rational numbers, and then outside of that, you had irrational numbers, and all that together is the real numbers. But the truth of the matter is, there's an even bigger universe than that. And that's where complex numbers come in. Because all real numbers are just complex numbers with an imaginary part of 0. Right? So yes, even outside of real numbers, there's a whole universe of numbers. We can also write any square root of a negative number as a complex number. For example, -4 is taking the square root of that. Remember, that's the square root of 4 times -1. Well, there's a rule for square roots, or just any root, that if I multiply inside the root, I can actually split them up into their own individual roots. So I'll have square root of 4, which we know is 2, square root of -1, which is I, which leads us to 2i. So as we continue on this section, we're also going to be very careful on simplifying square roots. Okay, we got to be extremely vigilant in simplifying square roots. Okay, I can't just leave this as the square root of 18 times I. No, we have to reduce that. The way that we reduce it is that, take a look at the number itself. Maybe not so much the negative sign. But look at the number in between. Now, obviously, we take the negative out and put an I on the outside, because that's factoring out -1. But look at 18. Here are the factors of 18. 1 and 18, 2 and 9, 3 and 6. Other than 1, the only one of these factors that's a perfect square is 9. Okay? So I know that the square root of 18 can be written as the square root of 9 times 2. Using the same logic as before, I can separate these into the square root of 9 times the square root of 2. And we all know what the square root of 9 is. It's 3. So the square root of -18 can be rewritten as 3 times the square root of 2 times I. So especially when we get to solving quadratic equations using different methods, we are going to be very vigilant about simplifying square roots, whether I get a real number or whether I get a complex number. Okay. Now, moving on. Another cool thing about complex numbers, specifically with I, is that their powers follow a cyclical pattern. So look at this example here. I to the first power is obviously I. I squared is -1 because that's the square root of something squared. Exponent and square root cancel each other out. Now, I want us to be very clear. This right here is the most important part of this section. And of course, in the sections that follow, I squared is always equal to -1. So if you remember any one of these powers, remember this, okay? But anyways, I digress. I to the third power is really just I squared times I. Well, we know what I squared is. It's -1. So -1 times I is -I. Then I to the fourth is I to the third times I. Well, that's -I times I, which is -I squared. I squared is always -1, so that's -1, which is +1. And if I try to go I to the fifth, that's I to the fourth times I equal, well, we know I to the fourth is 1. Well, 1 times I is I. That brings me all the way back here. So starting at 1, you have this cyclical pattern of I, -1, -I, +1. So if I want to find the next 5 powers of I from this, so I to the 6th, I to the 7th, I to the 8th, I to the 9th, and I to the 10th. So I to the 5th is I, so this is -1, -I, +1, I, -1. It's going to keep following that pattern. Okay. Now, moving on to operations. Now, just like real numbers, we can add, subtract, multiply, and divide complex numbers. Addition and subtraction are very, very easy to do. You just have to make, so it's kind of like, you know how we do 1 plus 2x plus 1 plus 3x? Well, you would combine like terms, right? Add the ones together, that's 2, and then add the 2 and the 3, that's 5x. The same process applies with complex numbers. We're treating I, even though I is the square root of -1, we can also treat it like a variable. So you pretty much add the real parts together and then add the imaginary parts together. Now, I want to be clear. I plus I is not I squared. That's multiplication. We're adding. Instead, it's 2I, okay? So here's an example. I'm going to do 4 minus 3I plus -4 plus 3I. Now, why am I putting them in parentheses? I'm putting them in parentheses to distinguish them from each other. With addition in particular, it's not really necessary, but it is there to distinguish one complex number from the other. When you're actually doing your adding, you don't really need them there. So 4 minus 4, that's 0. -3i plus 3i, that's also 0. Okay. Well, actually, let's do one that's not 0. Let's take 5 minus 3i, and let's subtract this time. Minus -2 plus 4i. Anytime that you're subtracting complex numbers, this is why the parentheses is important. You have to take that negative sign and distribute it to both parts of your complex number, because you're subtracting the real part and the imaginary part. So this becomes 5 minus 3i plus 2 minus 4i. And then, again, combine like terms. 5 plus 2 is 7. -3 minus 4 is also 7. Anytime that we do any operations with complex numbers, your answers must be in that form. A plus B times I. Something plus something times I. It's got to be like that every single time. Okay. Now, when we multiplying complex numbers, just like adding and subtracting, like binomials and stuff like that, is also similar. We have to distribute and FOIL wherever necessary. For example, if I want to take a complex number like 3i and multiply it by -5 plus 2i, then of course we're going to distribute. So this is -15i. Distribute here. That's 3 times 2 is 6. I times itself is I squared. Remember, I squared is always -1. And of course, we want to put that in the form a plus bi. So that gives me -6 minus 15i. Okay. Again, you always put it in the form a plus bi or a minus bi, whatever. Okay. So yeah, you definitely want to distribute, and also FOIL, right? We should also FOIL. So let's say I want to multiply these things together. So -6 plus I times -6 minus I. All right. So let's FOIL this out. First, outside, inside, last. First, outside, inside, last. -6 times itself is positive 36. This is plus 6i. This is minus 6i minus I squared. So it actually turns out the middle terms will cancel. I squared is always -1. So that ends up being 36 plus 1, which is 37. Now, the cool thing about complex numbers is this. Look at this example. These complex numbers are almost exactly the same, except one's a plus, one's a minus. Sounds very similar to difference of squares, right? Well, you can actually use this to compute a sum of squares, or to factor a sum of squares, by using what's called a complex conjugate. There we go. For any complex number a plus bi, its complex conjugate conjugate is the complex number in the form a minus bi. So for -6 plus bi, its conjugate is -6 minus I. All right, so -6 plus I, its conjugate is -6 minus I. If my complex number is 1 plus I, its conjugate is going to be 1 minus I. If 3i is my complex number, then -3i is its conjugate. Because again, this is 0 plus 3i, so 0 minus 3i is the conjugate. For real numbers like 5, well, 5 is its own complex conjugate, because 5 plus 0i is the same as 5 minus 0i. Okay. Now, for sum of perfect squares, so let's say I'm taking a squared plus b squared. This is sum of perfect squares, or sum of squares, for short. Just like you have difference of squares, now that we know complex numbers, we have a sum of squares. So this can easily be factored to a plus bi times a minus bi. So you take your real part, your imaginary part, you square them, and you add them together. So using that same example, -6 plus I, -6 minus I. So the real part, my real part is -6. My imaginary part is 1. If I square them, -6 squared plus 1 squared, that's 36 plus 1, which is 37, which is what we had before. Okay. Now, why are conjugates important? They're important because we need them in order to divide complex numbers. Okay. So again, we already talked about talked about sum of perfect squares. It's there at the bottom. But when we multiply, when we divide complex numbers, what we're doing is we're multiplying the numerator and the denominator by the conjugate of the denominator. What this does is that it allows us to eliminate I from the denominator, which will allow us to put our answers in that complex form, a plus bi. So here's an example. I'll give you guys a couple examples. 9 plus 12i over 3i. Now, I mean, obviously, I could probably reduce this fraction, but I'm not going to at the moment because I want to go ahead and just multiply, divide like normal. So if 3i is my denominator, then negative 3i is its conjugate. So I'm going to multiply numerator and denominator by negative 3i. I'm going to distribute here. So that's negative 27i minus 36i squared. Remember, I squared is always negative 1. So, and then, of course, this is negative 9i squared. Again, I squared is negative 1. So what's going to happen here is, so this becomes negative 1. Negative times a negative is a positive. So I have 36 minus 27i over negative 9 times negative 1, which is positive 9. Okay. Now I'm not quite done because remember, I want that form, a plus bi. So that's what I'm going to do. I'm going to separate these fractions. I'm going to separate these fractions. I'm going to put them in this space here. 36 over 9 minus 27 over 9i. So I'm taking the I and I'm moving it outside the fraction. And of course, I'm going to reduce those fractions. 36 over 9 is 4. 27 over 9 is 3. So 9 plus 12i over 3i is 4 minus 3i. Let's do one more example. 2 plus 3i. I'll do it over here. I'll do it in this space right here. There we go. 2 plus 3i divided by 1 minus 4i. One minus 4i is my denominator, so I'm multiplying both sides by 1 plus 4i. Okay. Now I am going to flow here, but I'm going to use the sum of squares formula for this here. Okay, just so you know what I'm doing. First outside, inside last. So 2 times 1. Then I have plus 8i. Then I have plus 3i plus 12i squared. And I'm going to use the sum of squares formula. 1 squared plus 4 squared. Okay. Combine like terms here. I squared is negative 1. So that's 2 plus 11i minus 12. Over 1 plus 16. Combine like terms in the numerator and add the denominator. So that's negative 10 plus 11i over 17. And of course, now I want to separate my fractions. Negative 10 over 17 plus 11 over 17i. Okay. And of course, when you separate fractions, you're going to move the I outside of that second fraction.